hope that the participants are very happy and they are enriched with the lecture from the speakers from the different field. Now, following up the first day, now we are at the second day of the session. In fact, this is the last day of the session as well. Without any delay, today we are going to start the technical session directly. And during this technical session, we have got three speakers. Professor Indrajit Sharma from Assam University. After that, we have the Dr. Devashish Bora from IIT Guwahati, followed by Dr. Anand Pariwar from Sikkim University. And after that, we will have the oral presentation that will run parallel like yesterday. So, okay, so I would like to request our Father Principal, Dr. Father Jonatas Kujur, as the Principal St. Joseph's College Darjeeling and the patron of this same event, to kindly coordinate the session. Father Principal, sir.
Okay. Yeah. Good morning to all of you. Am I audible?
Yes, Father.
Hello. Yeah. Okay. So good morning to all of you.
Morning.
I hope you had a very insightful, thought-provoking presentation by different speakers yesterday. I, Principal of St. Joseph's, on behalf of the organizers, welcome you to the first session of second day International E-Conference on the topic Recent Advances in Physics and Material Science. In the first session, we would be focusing on the recent advances in material science. For this, we have three resource persons from different esteemed universities. It is my honor to introduce to you the first speaker of the day, Professor Indrajit Sharma from the Department of Physics, Assam University. Let me say a few words about him. After his MSc from Jammu University, he obtained his PhD on condensed matter physics Institute of Technology, Guwahati. His area of interest includes theoretical condensed matter physics, electronic structure calculation. He has studied about 50 publications in national as well as international journals, including chapters in books. He has supervised 7 scholars and they have awarded PhDs under his Krishnan Research Associate Fellowship 2003. Sir, indeed, we are honored to have such a great and vast experience in the field of physics, that is Professor Indrajit Sharma, to this. So I invite him to proceed with his presentation. The density functional theory, electronic structure calculation. Professor Indrajit Sharma.
Good morning to all. Thank you. Can you see my slides? Hello. Hello.
Yes, sir.
Can you see my slides?
Yes, sir. Yes, sir.
Huh?
Yes, sir. We can see your slides, sir.
Oh,
Yes, sir.
Can you start now?
Yes, sir. You can start.
Can you see my full slide now?
Yes, sir.
Something problem is there. Good morning all. So with your permission, I started my talk, And this talk is dedicated to Professor R.K. Thapa, my teacher, retired professor, Department of Physics, Mizoram University. This talk is density functional theory, electronic structure calculation. This talk aims to give the basic concepts of DFT used for solving many electronic systems or material simulation. So first, let's go to physics lab and nano lab. Everybody can hear me now? Everybody can hear? Hello, Amit?
Yes, yes,
Can
sir.
you hear me?
Yes, sir. You're
Okay.
audible, sir.
Yeah. Let us go to physics lab, nano lab. This is the research who is doing experiment. He wants to prepare some material. So he decided the components of the material and he prepared the material in the lab. Now, after preparation of the material, he has to characterize the material. So he has gone to many experimental labs room, UBE, SAM, XRD, all these things. Finally, he is feeling that my sample is correct or not, but he found that no reason. What to do? What to do, God? So I will repeat the experiment again. So he has to, the person is repeating the material, composition decided, characterize the material, and check the properties. But he could not get the result. So he has to repeat again. Now let us go to this cartoon. We know that materials are highly purity material and very cost. Sophisticated instruments are very costly methods. Their effective use is greatly lost. Resource of the scientist, time of work. Now we can ask questions. Can we generate the structure computationally, predict the properties of the desired material at acceptable level using the well-established theories? And then one set of experiment is so expensive. Now answer is yes. Let us go together, theory, experiment, and computation. Now let us see a very simple example, gallium arsenide. Gallium has 31 electrons, arsenic has 33 electrons. Together we have 64 electrons. So we have 192 variables. So x1, y1, z1, x2, y2, z2, like that. x92, y90, 192, z192, 192 variables. If you write down the Hamiltonian of these systems, it's very difficult to solve the Schrodinger equations. It's about to impossible. Now, let's go to these cartoons. In quantum mechanics, if you know the wave function psi, other dynamical parameters can be determined. But for this large system of electrons interacting many body, solving Schrodinger equation is not so easy. So then what to do? Oh, I'm confused. But a theory comes, density function theory, to rescue this kind of problem. Now, what density function theory says? In density functional theory, if you give me the particle density, if you give me the charge density, I can write down the total energy as a function of density. If I know the energy as a function of density, other properties can be determined. So life is simple. Now let us go this. So in DFT, if we know the charge density of the system, then Brown state total energy can be determined as a function of charge density. Since density is a function of only three variables, x, y, z only, it looks like solving a single particle equations, hence life becomes more simpler. Now let us have the feeling. If we know the density, how we can determine the properties? We understand the particle in the box energy is given by n square pi square plus L square. I use the atomic units, so E I squared M I cap as 1. This is the energy level of a particle in a one-dimensional box. This is the wave function of the electron in a one-dimensional box. Now, this is the formula to calculate the kinetic energy. Since the particle in the box is potential energy 0, therefore total energy is the kinetic energy. In terms of density, we can do a little bit solving these equations, and I can write down the expression for kinetic energy in terms of density. This is the kinetic energy expressed in terms of density. This is the kinetic energy calculated from the quantum mechanics. This is the n square pi square by twice L square is the energy level. Now let us go to this feeling. Suppose I have one particle inside the box, then I can find the energy as pi square by 2 because n equal to 1. then I can get 4.913. This energy are in Hartree, this energy are in the Rydberg unit. Now this is the density. This is the kinetic energy calculated from the density. Then error is about 17%. It's less from the actual value. But let us put 2 electrons inside the box. If I calculate the density, if I calculate the energy of the 2 electrons from this expression, I'm getting 24.7. Then this is the kinetic energy calculated from the density. You are getting 21.8, 11% error. That means error is becoming reduced. Now, if I put 3 electrons inside the box, then your energy is 62.92. If I calculate that, if I calculate energy in terms of density, then I'm calculating getting 60.09. Error is 9% reduced. It seems that if I increase the number of electrons, error is decreasing. That means we are approaching towards a correct value. Now, what we feel, if the number of electrons is more and more, the ground state energy is more and more nearer, accurate to the exact value. If we have the charge density of the electronic system, we could find the ground state energy. Now, our feeling is that, all right, I'm convinced, number of electrons is more, accuracy is more. If we have the charge density, ground state energy can be calculated. That becomes more simple. We can handle it. Now, let us see a general form of Hamiltonian for a solid structure. I'm considering m number of electrons here, and I'm considering m number of nuclei. If I write down the Hamiltonian of this n electronic systems, it looks like this. This will give the kinetic energy, and this is the electron-electron interactions. This is the external potential. Now let us go to the next slide. You see this is the kinetic energy, this is the electron-electron part, this is the external potential. Now this is the kinetic energy, this is the electron-electron potential, external potential. Now one theory, Weinberg-Cohen theorem says that this energy can be written as a function of density. If I write down the energy as a function of density, then I should have the kinetic energy as a function of density, electron-electron interaction as a function of density. Then this is the energy contributed from the external potential. Now, still life is very difficult. Even I could list this part, still life is difficult. Let us see. Now, from the Weinberg theorem, what I get the information is that energy as a function of energy alone is sufficient to determine the ground state energy and the ground state density. We need not to go all this part now. Now let us go this one. Still, we have difficulty to solve it. How to do density function theory comes to rescue this issue. Now let us see how to resolve the issue. This is my actual system. These are my interacting electron system, which I have written before this. To solve this, I have to consider a mimicking system. What is this? The mimicking system is that I assume that this is the electronic system, but there is no interaction. But one condition is that there is no interaction and the charge density of this actual system is same this system with this mimicking system. Now I represent the kinetic energy of this non-interacting system as T naught. Then this will be moving under a potential, and let us see how it looks like. This is my actual system, interacting system. This is my mimicking system. If I assume that my mimicking system, then how to write down this energy function is the question. This energy function can be written as T naught rho. I already told this is the kinetic energy of the non-interacting system. This is the Hartree energy. This is the exchange correlation energy. This is the energy contributed from the external potential. What is correlation energy? How to define the exchange contribution energy is another lecture. It will take a lot of time. So I will skip how to calculate the exchange correlation energy, how to calculate the correlation energy. In simple, correlation energy is the missing energy in the kinetic energy of the actual system and my mimicking system. Now, this is the energy function of my system. I already tell this is the Hartree energy. This is the exchange correlation energy. If I do the differentiation with respect to rho, I can get exchange correlation potential. This is the Hutty energy. So everything I can calculate in terms of rho. Now, if I write down the Sojgen equations like form of this energy expression, I will get like this. This is the kinetic energy of a single particle. This is the external potential given by the all nuclei. This is the Hutty potential, which is given by this. This is the exchange correlation potential. This phi r, phi IR are called the quantum orbitals. And this quantum orbitals can be connected to the density. Now let us see quantum equation. These quantum orbitals could give the density like this. Now all these things I can, these are 1, 2, 3, this potential, all these 3 terms are potential. So collectively I call it quantum orbitals. Now I want to little bit simplify. The simplification is this. Instead of that 3 terms potential, I put the quantum potential. Then if I solve this equations, then I can write down this E1 plus E2 plus E3 plus dot dot up to occupy. Then this will be kinetic energy part. Then this will be the energy corresponding to the potential. This E1 plus E2 plus E3 plus till EM occupied. Then I can get the energy of this part is kinetic energy of the non-interacting. This is the potential quantum or potential I call it now, and this is the energy contribution. Now I have this expression already. I have shown in before slides. Now I want to replace this external potential in terms of BKS. If I do this, then this BXT will be replaced by this expression. If I replace this expression, I will get this term. This term I can put as this one, and I'm putting this one as it is. Now, this final expression for energy function for computation calculation, this would be calculated. This EM, this E1, E2, E3 will be calculated from the quantum equations. Now, next issue is exchange correlation energy. The unknown exchange correlation energy must be approximated. There are different methods to find exchange correlation energy, but here I will be picking up only LDA and DGA. LDA is called local density approximation. This is called generalized gradient approximation. Now, LDA I only call local density approximation. These exchange correlations in LDA approximation can be written like this. This small ex is the exchange correlation energy per particle. The difference between LDA and DGA is this. This exchange correlation energy per particle depends only on the density. And the generalized gradient approximation, here exchange correlation energy per particle depends on the density, also gradient of the density. Therefore, this is called generalized gradient approximation. There are different methods for the LDA also, regular, this Hedin, Lubitz, Purdue, and Wang. Purdue and Wang is the most used one. In the JGA also, these two are the most popularly used. People use PVE, 98, all these things. So we skip the mathematical expression for various LD and GGA. This will be another lecture, how to calculate LD, how to calculate GGA, completion, all these things. So I skip right now in this lecture, how to do the LDA, how to do the GGA. Because I pick up the expression and fit to the calculation. Now, issue is over. Now comes to the computation part. The computation part is I use Win2K. Win2K is very popular. Many people use it. And how to use the Win2K is another part of the lecture. So I will not go in detail how to handle the Win2K. I will try to present some results of the calculation using Win2K. Now, some result calculation of the Win2K DFT, I pick up gallium arsenide. You see, gallium arsenide exists in 3 structures, zinc blendy and the rock salt structure. And this is the zinc blendy structure and the rock salt structure. But how you generate, how you do the volume optimization, it is more important to understand the basics of DFT. Now, suppose this is my unit cell starting. Some part you make it larger. What I'm saying is that this 5% you make it larger, 10% you make it larger, 15% you make it larger. Calculate the energy of this larger part. On the other side, you reduce the size, minus 15%, minus 10%, minus 5%. You calculate total energy, what we have expressed in the density functional theory. If I get all the energy, then I can plot with respect to volume. This is the plotting of energy versus volume. Now I have two structures, zinc blende structure and the rock salt structure. Now energy is minimum in the case of zinc blende structure. That means that gallium arsenide structure in zinc blende structure is more stable. Lower energy is more stable. This is the zinc blende structure. This is the rock salt structure. Energy is minimum in case of zinc blende structure as compared to rock salt structure. So therefore, we consider the zinc blende structure is the stable structure. Now this is the just a data. This is calculated lattice constant for the volume optimization for the zinc blende structure and rock salt structure. As comparison is given from the experimental and the theoretical calculation. These are the. Now, yesterday also we have seen some phase transition. Since there is a zinc blende structure and rock salt structure, we could study the phase transition. Phase transition can be studied in two ways. One is putting the temperature, one is putting the pressure. But in density functional theory, generally we do the phase transition under induced pressure. So let us see how it is doing. So we understand that at the phase transition, this enthalpy should be same. Actually, this is drift-free energy, T plus PB minus TS. But the density functional theory is calculated at absolute zero temperature. Therefore, the temperature part we put 0. Therefore, drift-free energy same as enthalpy E plus PB. Now we understand that at the phase transition, this enthalpy should be same. So now this is the enthalpy versus pressure for the zinc blende. This is zinc blende and the rock salt. As we already mentioned that enthalpy should be same at the transition pressure. So here is the point where enthalpy is same, and this gives the corresponding transition pressure. Therefore, in this calculation, we can say that this transition is 10.7 GPa. Now, this is the data which I have shown in the graph, and this is the volume collapse. That means there is a volume collapse from zinc blende to rock salt is 14.2%. So now this is the band structure of the gallium arsenide in zinc blende structure and the rock salt structure. In this band diagram, we can see that the top of the valence band and the bottom of the conduction band are in the same line at the gamma point. These points are called high symmetry points. I will not go in detail high symmetry points, but we observe that this top of the conduction band, bottom of the conduction band, top of the valence band are in the same line at the gamma point. That means it gives me a good information is that this is a direct band gap. And the band gap value is about 1.3 electron volt. But in case of rock salt structure, there is a interaction of the conduction band, crossover of the conduction band towards the valence band. Therefore, it indicates that this is a metallic nature.
Excuse me, sir.
Yes. Yes.
Yes, sir. Sir, you have only 5 minutes
Hello.
left.
Okay.
I will to wind up.
I will try to wind up. And this is the dose of the sample. Dose of the sample says that which orbital contributes to the valence band, which orbital contributes to the conduction band. Here you see this is a -6 band. This -6 band is corresponds to here. Corresponds to here, and this is the -10 band is corresponds to here. So this we can see that these are contributed from the SPD gallium, SPD arsenic. Now this is the band structure as increase the induced pressure. I will not go in detail. Now I will come little bit about the elastic properties. In PV crystal, we have the 3 elastic constant. How it is calculated? This is what I want to mention here. These are the stability condition. So to calculate the C11, C12, C4, we need minimum 3 equations. How to establish that 3 equations? The 3 equations could be established. One I can find easily from the bulk modulus. One I can find the volume conserving autonomic strength. This is energy with after strength. This is energy before strength, and this is the V naught is the volume of the optimized volume, and this CS is given by this one. And another third equation we could get is volume conserving monoclonic strength. And with these 3 equations, I can find out the C11, C12, C13, C4. Now, in the elastic properties, what are the properties generally people study is general anisotropy factor, Poisson ratio, Clement parameter, Young's modulus, Debye temperature. Already I could calculate C12, C11, C44. I can calculate the general anisotropy, Poisson ratio, Clement parameter, and the this. Why we are calculating? If I calculate the general anisotropy factor, if I found A equal to 1, I can predict that material is elastically stoppy. If A is greater than 1, I can say that material is stiffest along body diagonal. If A is less than 1, I can say that material is stiffest along body edge. Similarly, other parameters can give the information about the elastic properties. So I will come little bit data of the elastic properties of indium phosphide. This is the B by G ratio. From the B by G ratio, we can say that the material is brittle, material is ductile. And this is the Poisson's ratio, Clement parameter. If I say that this is a Poisson ratio 0.2 to 0.28, immediately I can say that this is ionic bond is more dominant. The Clement parameter I am getting around 0.59 to 0.77. That means it is approaching towards 1. That means the material is more easy for bond stretching. If Clement parameter is 0, then I can say that material is more easy for bond bending. So looking to the values of this Clement parameter, I can say elastic properties of the material. Many things I can talk about these things. Now, this is the Poisson's ratio, Clement parameter. Just now I have shown to you. Debye temperature, Young's modulus. Young's modulus can be correlated to the rigidity of the material. If Young's modulus is more and the more, rigidity of the material is more and more. So what I mean to say in conclusion is that using the density constant theory, calculating the elastic constants, we can study all the elastic parameters. So with this, I thanks to all. I do special thanks to Amit Shankar and R.K. Thapa, Professor, Physics Department, Major of the University. Thank you all.
Thank you, sir. Thank you for the well-structured presentation. Physics ones, so I not be able to give a brief summary of it. But in spite of the clear presentation, I'm sure the audience will have some questions, some clarification to ask to you. Since we are running short of time, we will maybe questions. So the floor is open to the participants to ask questions to Professor Indra Sharma.
Yes, good morning.
We'll take one.
Good morning, Father. I have a question. Yeah, I'm Professor R.K. Thapa.
Yeah.
Can you hear me, Father?
Yes.
Hello.
Yes.
Yeah, it's not a question, but then first I would like to, good morning, Father. Thanks for giving me this opportunity to ask one, not to ask a question, but rather just to thank Professor Indrajit for dedicating this talk to my name.
Yes, sir.
This is a